about the algorithm to use the Lat theorem to find out all the circuit and path. Then depending on your objective here, if you want to find out all the circuit, then you choose, run the vertex and you do the second step like this one to find the connection drawn to another vertex. So that is not a cut, not a cut tapping connection, but not a cut edge. Okay, and then you remove that one and you extend the Euler. Okay, the Euler. So let's apply that theorem here. So we apply exactly. I mean, the theorem is more important than the algorithm in this case. The concept in the theorem and the idea in the theorem is much more easy to check, and that gives you the answer for this. Today, actually, the difficult problem is not about the Euler, but about the Hamilton. And in terms of application, then the Hamilton is much more useful. At least it can be applied to the traveling salesman problem, shortly TSP. So the TSP or the traveling salesman's problem here asks you to find a shortcut route for some people, traveling salesperson. You are agent from some company, you sell the product for the company, and you want to visit many cities, let's say in the southern part of Vietnam here, maybe your central branch here in, let's say Ho Chi Minh City right here, you see, and you want to travel to visit many branches in the entire region, okay? And because of budget, you should plan your visit only one city. You must stay only one time. You see, so that means we talk about Hamilton here. We talk about the traveling salesman problem. We don't regard the connection, but we regard the vertices. We consider the path, the route, the journey you design, you plan for your trip. Actually, are concerned about the knot or the vertices inside the graph, because the cost to stay at the hotel overnight is costly. So we concentrate on the vertices in the Hamilton, while in Euler we concentrate on the edges. Okay. So that's why we say here, the TSB finding the shortcut route in the sense minimize the cost to stay at the city or at the vertices in the graph. One city, one night only, you see. Not allowed to stay in some city a few times, no, only one time. Then we can formulate that one by using the Hamilton graph concept. Okay? A tour means, a circuit. We consider to be a circuit, right? The tour mean in the normal life, in our real life, we say a tour. But in mathematics, we say a circuit. So we start from Ho Chi Minh City, you travel a few days, maybe a week, to many the city. So let's say if you have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, let's say. So imagine that you have 11 cities, and that means your circuit or your tour must be a kind of cycle. You start from Ho Chi Minh City, you travel many times, and finally you step back to Ho Chi Minh City. You see, and this is Ho Chi Minh City, for instance. And although there are so many connections, but you don't need to employ all one connection, because you focus on the node on your chip only. You see. Then we ask ourselves, is there any way to find out such tour? Okay, and that we call the DSB problem. And to solve that, we need this concept defined in Hamilton circuit. So we have a graph here and a node here and a Hamilton circuit, a circuit inside the graph that visits each vertex in the graph once. If you can find out such Hamilton circuit, then the graph G itself we call a Hamilton graph. The problem is, how can we find Hamilton circuit? To find out Euler circuit, very easy by the mathematics I mentioned a few minutes ago. But so far, until the 21st century, there is no concrete algorithm to find out the Hamilton circuit. So this is the fact you have to keep in your mind. Although we define the concept Hamilton circuit very short, very compact, very clear in this way. But find out this one in draft in general is not fully shown. Okay, but we can make some observation here. If the Hamilton circuit exists, we assume that if this one exists in your draft G, then by definition, the vertex set of the Hamilton circuit must be exactly equal to the original vertex set by definition. Okay, because you read here each vertex in the graph G. So the circuit visit that, so that means we have this identity. And so furthermore, because you visit each vertex only once, that means somehow the circuit Hamilton here actually can be thought to be just say a cycle Cn inside the original graph G. You remember? Because the graph G can have much more connection, where the C phi here consists exactly n connection. Remember? And the Hamilton circuit somehow can be identified to the Cn thought to be a subgraph of G. Therefore, if you employ that, then you get the second one here. You see? So this is our first observation to determine the Hamilton circuit. So the two properties here very useful. Okay, but the problem is to find out this one is not simple for large graph. That means where this one somehow big number. Okay, few thousand nodes. Because if you have only 3 nodes or 5 nodes, you can find out by hand. But if the number of nodes, let's say, well, you talk about the graph and maybe 10,000, that means 10 power 5, you see? Well, this is 100,000 actually, 10 power 5, that means 100,000. So, you need algorithm to find out. And the answer is not. Okay, we have some certain condition, but not full. So let's say the first example, very simple here, where I give you a graph with only 1, 2, 3, 4, 5, only 5 vertices, and this one must be connected, of course, and you need to find out a Hamilton circuit. See that? And by definition, you have to start from any node, because this will form for you Cn, and you remember a circle graph go through all vertices, right? So you can start from any node inside, and you go. If you employ A, then you don't employ A again. By definition of Hamilton circuit, you go to B. And if you employ B, then you never go back. You cannot go back to B. You have to go to the next one somehow. In this case, very easy, because the Hamilton circuit is exactly equal to C phi. Like this one. This is C phi. And you see that the condition here fulfilled, right? The vertices inside the Hamilton circuit is exactly equal to the vertex set of the original graph. And furthermore, the number of HC inside the Hamilton circuit is exactly to be number 5. You see, 1, 2, 3, 4, 5. So I mean, we can solve for smaller graph very fast. But well, can you do this one here? Well, you cannot try in 2 minutes. You know. That means we need to figure out an algorithm. Although the methods are the same, but if you have more possibility in your root, then the problem will cost your time. But first of all, let's observe how many n here, how many vertices. The outer part we have 5, the middle part you have 5, that means already 10, and after that you have the inner part another 5, and there are some certain point here another 5, so that means about 20, right? For round, for layer 1, 2, 3, and then 4 layer. But the number of edges is very large, at least more than 20, you see. So you cannot trial and error like you did for the left hand side. The right hand side graph need to be thoughtful, carefully find out. But again, if I give you half an hour, then maybe you can find very fast. If you choose here the starting point and you go obviously the first strategy should be go through all outer vertices and here and finish 5 vertices in the first layer and go deeper in the second layer. You see the second layer, and either you continue or you go to the third layer and then you go around with the third layer, and then you finish the 5 vertices in the third layer and you go back to the second layer, you see, and we go there and we go there and we go to the vertices, this one and that one, and you go over every vertex in the second layer and you finish, and it turned out to be the right answer. Again, trial and error work well for up to, well, graph like this, but imagine in future you have few thousand. Well, then let's see. And I told you that no algorithm to find out, to determine like the Euler. The picture here show you the second way to solve the two graph. So I will skip this one very fast. Then because we don't have the necessary and sufficient condition at the same time, I mean no equivalent condition for Hamilton circuit, therefore we have to formulate the necessary condition first. Necessary condition mean if you assume some Hamilton circuit already exists, then what are the property of that circuit? You can list all the property, and those property we call the necessary condition. So if some structure satisfy the definition and the feature you obtain from that, we call necessary condition by logic theory. Okay. So that means here we assume in some graph we already have Hamilton circuit. So this is the first part. Then the property you observe here, always true. First of all, any vertex in the graph having at least degree number 2. That would be true globally, every vertex inside. And that's it for sure, okay? Because if the Hamilton circuit go through them, then we employ at least 2 conditions to any vertex V, you see? Secondly, if we look locally to that particular Hamilton circuit only, okay, inside the Hamilton circuit, you don't need to employ all connection, then the degree of the vertex inside that local Hamilton circuit must be number 2. That means you employ 2. Maybe the degree of V locally to be number 6 or number 5. But if you look locally to that Hamilton circuit, you must employ 2 among the 6 or number 5. You see? So that means the property 1 and 2 here is obvious for any Hamilton circuit. So we go fast a little here to design the rule number 1. This one is already proved by definition. Now we derive the first rule saying that if globally in the entire graph the degree already equal to number 2, then you must employ all number 2 condition to that. Okay, that's clear, right? Because we employ the second condition here. All of the condition must be utilized in the Hamilton circuit. I mean, you don't have the necessary and sufficient condition the same, so we explore this one first, necessary first, then we design the rule. So like the picture, you see, the vertex V, degree 2, then the Hamilton circuit must go through that vertex V by definition. Therefore, we go through up and we go down here. So we employ both by this figure. I mean, studying Hamilton circuit to me is more interesting than the Euler, because there are something not yet clear. The second rule saying that no sub-circuit can be formed in the trap. So let's see some illustration for this. No, not yet. So the third rule saying that 1, 2 connection at a specific vertex already determined. So like this one already determined. Then you don't use the other one. Therefore, on other SC incident that means connected to V can be now removed. Okay, because you already utilize the vertex V already to find out the circuit, Hamilton circuit. So that means this one, that one can you employ. That's enough. The other one will be useless. Useless. That means not usable at all. Therefore, you can remove. So let's see the idea, and we can draw the picture here to illustrate. So this is assuming that degree of V to be number 4. You see, and you want to find out Hamilton circuit going through V. You see. Then let's say we go from the left upper in and we go out from the left lower here. So go in here and go down there. Then the right, the two on the right of V will be useless, then remove like this one. You see, because the not V already utilized to form the Hamilton circuit. So rule number 1, number 2, number 3 are very useful. Okay. Okay, Wang going for some lecture. Okay, that's okay, Wang. So I will show you this particular example, and hopefully you see the idea. Okay. We start from G. Okay. This is a connected trap, and the vertex means the city, and the H means possible root, and the degree of G already number 2. Therefore, I employ both connection to G. You see the extension, right? And then we continue from E and I, the not E and I, but the degree of E and I are bigger than 2, so we choose the minimum one, which is the not I here, and degree to be number 3. So we already employ the GI, so we don't employ GI again. So we have to define the left or the right of I. We choose go into the left, so we have IJ. You see, IJ going to the left, so we remove IK on the right. Then we extend, right? Continue that from J. So we end up right now at the node J. Then we continue the story from J. And you know, when you finish at some vertices, you have to remove the redundant, okay, connection from that node. So we got to J and we continue from J, and again idea, you see, the node K will be the next one because we apply the rule, second rule to not J here, connect to RK, and from K we go up to H. So that means the vertex K already employed, but the vertex X here you have degree 3, you have to choose either go up to C or go to the left. But if you go to the left, then you finish the roots not good. Therefore, I want to go up, I think, to extend higher to make sure that the one there, and at the same time here the J you employ GI, so you delete the GF here, and I mean we can do at the same time to make sure that the three rule number 1, number 2, and number 3 fulfill, you see. And because I thought that the ES not useful, you don't need to use, so we go up from here. The not E here has degree 2 enough, so this one disconnected and this one go up. I mean, just repeatedly employ the 3 rule 1, 2, and 3. Then the Hamilton circuit will have bigger and bigger vertices inside. So on the way, don't forget the last rule, very important. So for instance here B degree 2 already, so we don't employ BD, you did it out, you see. So things like that, you see, I remove the BD, clear? And when we remove BD, then the not D must be determined because this one down to degree number 2, and by the first rule, the knot D must be inside the Hamilton circuit. So that's why we circle the knot D. I mean, apply at the same time the 3 rule for entire normal draft, and we employ AD and C, and finally you see every vertex cover, you see, every and the AC redundant, so we remove AC, and finally you got the Hamilton circuit. So although we explain long like that, but by computer you can find very fast if you can apply the 3 rule at the same time. So you could play this one with the file I upload to the web to see the idea about employing the necessary condition. Necessary condition of Hamilton circuit, but not sufficient, remember. So right now we not yet talk about the sufficient condition. Necessary condition means the one you obtain from an assisted Hamilton circuit. So therefore, because the two necessary and sufficient not occur at the same time, so we conclude here the Hamilton circuit does not exist for all graph. That means that structure exists for some certain graph only. Okay, and the second one is that I told you before, no specific way to find out the circuit or not exist or not. So that's the problem. Okay, so we have to check by the rule I mentioned before. So there are 3 rules about Hamilton, and the second rule say no sub-circuit, and you see here if you count in the outer part, you have this one to be one circuit, you see, but this one consists 2 sub-circuit, namely the left or the right. So the second rule say no exist Hamilton circle, because you see this one is contradict to what we define the internal part here. The center here already employed so many times, so that contradict to definition. Okay. Therefore, we move to the second half of Hamilton circuit, namely, we talk about the way to prove Hamilton circuit does not exist. There are many theorems here. Actually, we list only two theorems, the most two famous. Okay, but let me remind you again about the concept here. To prove does not exist, similar to the graph invariant. Okay, you need to check some certain necessary condition to be violated. Because again we employ this logic equality. If Hamilton exists, then the necessary condition fulfilled. Therefore, if certain necessary condition not fulfilled, then the graph does not have Hamilton circuit. Therefore, if you want to prove the Hamilton does exist, you have to provide some other condition, not using the necessary. Because if you employ that, only one way to prove not exist. Okay, so to find out or to prove, to make sure that the graph exists, you have to find out different condition. Okay, we call the sufficient condition. To prove not, then easy by showing that the necessary condition not fulfilled. But to prove yes, you have to find other condition. Okay, and so far until now, in the last 60 years, not much improved in terms of to find out the condition are both necessary and sufficient. The necessary condition and the sufficient condition are different set when we talk about Hamilton. Okay, so I will move to the sufficient now. They are two famous theorem. Actually, there are about 10, but at least in your class only two. Okay, but before that, I will make two notes here. The more edges in the graph, then the more likely that the graph to have a Hamilton circuit. That's obvious by definition. Secondly, if you put extra edges into the graph, but you don't add more vertices, you keep the same original vertices, then you hope you can produce a graph to have Hamilton circuit. So the two are not here very important. And actually, so give me about a few more minutes and we finish. I would like to finish this slide today. Okay, the first one by Dirac here. Okay, Dirac actually is not the famous quantum physicist. No, this one is the son-in-law of the famous. Again, so very bad connection today, guys. Lost connection again. So very worse today. A few more minutes, guys. We finish this slide. So bad connection today, but be patient. We are talking about the two theorem provide sufficient condition. So the first one, the vertex here in the graph on way at least n divided by 2. So this is the first, okay, 1952. Every vertex must have degree at least like this. Secondly, if we talk about the pair of vertices, then the sum of the degree must be at least number of n. Okay, so every pair of non-adjacent vertices. So we can employ theorem by Dirac and theorem by Orr to confirm that the graph having Hamilton circuit. To me, this one is very beautiful. I mean, the first theorem, when I was young, when I the first time studied graph theory, I remember my thinking was that the theory very simple. Okay, so you have a simple graph with n vertices, and you check for every node inside. If you see that the degree at least n by 2 and divided by 2, then you say, well, this one exists Hamilton circuit. And today would be enough because we lose a few connections. I worry if you have another class, so therefore we finish the theory at the Hamilton circuit and we discuss about application next week. Okay, do you hear me well, guys? And if you want to have question, I mean, we cannot finish this long lecture in one day, so that means we design this one for 2 days. Okay, today and this Thursday we continue. Okay, from here about